Well, I will get started here. Let me, before I forget again, give you guys this exciting attendance sheet, which I printed out like 2 days ago, I think. Ah, very good. Alrighty, I will pray. Dear Father, we thank you for this day again. I thank you for this class and this time we have to meet and study your creation. Just pray that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. Do you guys have any questions about anything before I get into the stuff? Yes, no? Well, if you think of some, you can ask them. So I always talk about how would it go if we had something like this, right? And suppose you got, let's say, a hole here, and another hole here, and another hole here, all right? If this was the region we're looking at, can we do Green's theorem for this? You know? So, in other words, is it true that the double integral over R of partial Q, partial X minus partial P, partial Y, dA, is that still equal to the integral over the boundary of R of P dx plus Q dA? I mean, Q dy rather. And so we did this yesterday for a single hole. What if we have multiple holes? How would that go? Yeah, there. What if what can we do? Any ideas? What if we, I don't know, like make some cuts, right? Like, I'll start here. Let's see here. I guess I could just cut this in two, can't I? I think I can still just cut it in two, right? If I make a cut here, and then here, and then here, and then here, if I make these cross cuts, then if you look at what's above and what's below, those are simply connected, right? In the sense that, what I keep talking about simply connected, what do I mean? I mean, if here's a loop, right? If it's simply connected, I can just take that loop and continuously deform it without leaving the space to a point. In simply connected space, I can deform continuously a loop to a point, all right? Now, I can't do that on the original space because if I encircle this, I get stuck right on that, right? I can't squeeze past the hole, all right? So that's not simply connected if we include the holes. But if you just look at, oh man, I messed with my picture now. But if you just look, you know, at the region that's above the blue crosscuts or below the blue crosscuts, any loop in those spaces, right, we can deform to a point. So the northern and the southern region in my picture, right? There we go. Are simply connected. Now, what do I mean by these crosscuts? What I'm saying specifically here, all right, let's think right-hand rule. So I'm saying down here, we're going like this, all right? But I'm also, for the below, going the opposite way, right? And you see, if you look at that, then I've got like this kind of, if I continue this red, for the lower half, I'll get like that, right? But on the upper half, I got what? Like this, right? Right? And then continuing, right, we go all the way around. Wait a minute, I did that wrong. Oh, come on, have I done it again? Oh, good grief. Come on. I keep doing this. I'm sorry, guys. This way, right? I wish you guys would stop me like 3 minutes ago. No, there's no secret. It's the same thing we did yesterday. All right. I am sticking to our convention. So could we do other things? Could we make other conventions? Sure. But we're sticking to our convention, which is that we want to positively orient. We have written down Green's theorem for the positively oriented edge. And so if we imagine ourselves as like a little dude walking along the edge, right? Then in the directions that I'm currently drawing, right, like this, if you imagine yourself a little dude, and he's walking along on his left, right? The left is the inside. Likewise up here, if you imagine yourself a little blue dude walking along, this way. Wait a minute. Well, that's a, I didn't fix that one yet. You guys got to stop me. So we're supposed to be walking this way, right? Right. Right-hand rule. Out of the board. So our fingers should be like curling like that. Now inside, these are what? These are doing what? Like this, right? So these are clockwise, right? So we have to understand that this boundary of R is the boundary of the outside part union with the boundary of the inside part, right? And the outside part is counterclockwise oriented, but the inside part is clockwise oriented. That's the convention. We derived this last time, right? Because I assumed both the outside and the inside were counterclockwise oriented, and when we did that, we got the difference of the outside from the inside, right? So we absorbed that minus into reversing the inside curve into the clockwise sense, and that gives us this additive result as opposed to the difference. So anyway, my point to you is we can extend what we did last time to multiple holes. It still works, okay? Yeah? We just have to clockwise orient the inside edges and counterclockwise orient any outside edges. Does this make sense? I hope. Yeah. All right, so an example for us that I should work is find the area bounded by x squared over a squared plus y squared over b squared equals to 1. And oh, okay, that was it. I guess I can, I'm thinking of a different example. Oh, I see. I got two examples. All right. And x squared over c squared plus y squared over d squared equals to 1. All right, so let me draw a picture of what's going on here. So I intend for like a, so like x goes from plus or minus a. All right. And let's say y goes between plus or minus b here. All right, so that's this ellipse, right? But on the other hand, I want to imagine the other one. The other one, we will imagine larger out. Like x goes between plus or minus c, let's say. I mean, that's what I've written here. And the y goes between, you know, d up here and minus d down here, right? So we've got this outside ellipse out here, right? So we're trying to find, I'm trying to show you how we could find the area between the ellipses. All right. Using Green's theorem. Of course, we could just calculate the area using our previous methods, right? That'd be, I mean, you could do that. Although, it's a little bit awkward here because the change of variables for the inside ellipse and the change of variables for the outside ellipse are kind of different, right? I guess that's kind of something you face with this no matter how you do it, but I'm trying to find the area in here, right? All right. And the question is, how do you find area, right? So I need to mention something. So remark. If we look at the vector field F equal to 0, comma x, or if we look at the vector field minus y, comma 0, or if we look at the vector field x over 2 minus y over 2, all right? All of these, right? So if we, you know, think of these as f equals to pq, right? As partial q, partial x, minus partial p, partial y, equal to what? For these, all three of these choices. I probably should have made this remark before I started the example. I'm sorry, I kind of got things out of order here, but you guys can bear with me. What's that? They all have what? This is what? Not 0. No. 1. Yeah, 1. It's 1. So it's either 1 minus 0, which is 1, or it's 0 minus a minus 1, which is 1, or it's 1/2 minus a minus a half, which is 1. Is this it? How many different vector fields are there such that the, you know, partial q, partial x minus partial p, partial y is 1? There's infinitely many, right? But this is just 3 nice choices. And the point is, in view of this, that if we have the, you know, the integral of p dx plus q dy over the boundary of some region, well, that's equal to the integral over the region, right, of partial q, partial x minus partial p, partial y. But what's the deal? Well, for these vector fields, that's just dA, right? It's literally the area of R. So I illustrated this idea last class with that the shoelace formula. We were able to calculate the line integral to calculate an area. Yeah.
Do you have that last vector field what should be negative y over 2, comma x over 2?
Oh, is that? Yes. Thank you. So that's why you guys told me 0. I think it's supposed to be, yeah, minus y over 2. Yeah, x over 2. Like, if you look at the last example we did last class, we integrated like 1/2 of x dy minus y dx from last time. That's what's going on there. Thank you. So listen, there's 2 different ways to go with Green's theorem, right? it's a bridge. It's a bridge between two worlds: the area integral and the line integral, right? So we can either use the Green's theorem to simplify an ugly line integral, trade it for an area integral, or we could also alternatively calculate areas directly using the line integral, which is interesting, right? So now, as we apply it to example 1 here, we have the boundary. If this is my R, right? The boundary of R is what? It's, ellipse 1 union with ellipse 2, right? And so ellipse 1, we could put x equals to a cos t, y equals to, and I should be careful. If I'm going to make these, and I do want to make these, I want to make these ellipses counterclockwise oriented, because that's the natural way to write formulas down, all right? So if I'm going to do that, I shouldn't put, if this is E1 here, right? And this is E2 out here. E1 has to be, and I want, my point is the boundary of R, I need a minus E1 here, right? Because that, if I'm thinking of E1 as counterclockwise oriented, as I am with writing these formulas down. See, these formulas, the standard parameterization of an ellipse, those go counterclockwise. As t increases, your sweeping angle in the usual sense. So that's the E1. Now E2, I can parameterize by x equals to c cos t, y is equal to d sine t, right? Now, we can use any of these that we like. We could use this one, or we could use that one, or we could use that one to calculate these. What do you guys want to do? The easy one? Well, I mean, there's a certain easiness in this because there's just one thing, So it's, but if I think through it in my head for a second, which is dangerous for reasons I'll explain, this would be like, a cosine, and then the dy gets a b cosine. So I end up integrating cosine squared with this. I think I end up integrating sine squared with that. I think I end up integrating sine squared plus cosine squared with this one. I think we should go with this one. Yeah, that's the one. So, all right. So if we look at, is that?
Is the vector field for those or whatever, was that given, or how did you find that?
This is a remark. So
Just in general, that exists, so...
if you want to calculate area with a line integral, you want to find a vector field whose partial q partial x minus partial p partial y works out to 1. These are 3 vector fields which give you this is 1, which allow you to calculate the area by calculating the circulation of the vector field. Yeah, there's other choices, yeah. But these are the 3 popular ones. Okay, so let's do it. I'm gonna do E1. So we're looking at the integral of I'll put the 1/2 up front, right? 1/2 x dy minus y dx, yeah, over E1, which is 1/2 integral from 0 to 2 pi of x, which was a cos t. My dy is b cos t, and then I've got minus b sine t, and then my dx is a minus a sine t. Big old dt out here. And so lo and behold, we have a b over 2, the integral of cosine squared t plus sine squared t, dt from 0 to 2 pi, which of course returns to us pi ab. So we could have done that by its lonesome, right? We could have just calculated the area of the ellipse, just doing this, right? That's one thing. But I'm interested in the area between the ellipses, right? So the area of the R we're considering is going to be, the integral of f dot dr over E2 minus the integral over f dot dr over E1. And here my f, of course, is 1/2 minus y comma x, okay? I just don't want to write that out 2 more times. I just want to get to the point. So we just worked out that the E1 integral is pi ab, so by the same calculation, the outside integral is what? A is replaced by c, b is replaced by d, so it's just what? Pi cd. So we get pi cd minus pi ab, and so we get pi times cd minus ab. That's the area between the ellipses, which of course makes sense, right? You just you subtract the area of the inside ellipse from the area of the outside ellipse, and that gives you the area between the ellipses, right? Make sense? I think it does. Yeah. This is still a really weird way to calculate area, though, right? I think. Pretty weird. Any questions or no? All right, so let me remind you that while Green's theorem is interesting, we're still working on the question of what is a conservative vector field and how should we understand it, right? So now that we have Green's theorem, let's circle back to the question of conservative vector fields and see if we can understand them more deeply, right? So let me remind you the statement that we had before about conservative vector fields. So we had the following are equivalent, right? Number 1, f equals to the gradient of f on U, right? Which is a subset of Rn. Number 2, we had f is path independent. Number 3, we had that the integral around a loop is 0 for any loop in U. And number 4, with n equals to 3 and U simply connected, I said that we eventually would attach here, with that precondition added, we could throw on the pile here the curl of f being 0. This is what we said before. All right. Now, this is the following are equivalent. That's what this means. The following are equivalent. These are 4 seemingly different characterizations of what we mean by a conservative vector field. Number 1 is my definition. All right. So let us specialize this discussion. Instead of looking at n equals to n, let's look at n equals to 2. After all, that's where Green's theorem lives, right? So let's now specialize to 2. All right? 2 dimensions. Everything's pretty much the same here. If we replace this with n equals to 2, U simply connected, that's still a thing. But instead of putting this condition, like this gets replaced with the simple equation what? In our current context, this just amounts to partial q, partial x minus partial p, partial y is equal to 0. Now that's a natural consequence of that, you see, because if we look at the vector field f, which is p comma q comma 0 in 3 dimensions, right? This vector field, the curl of f, it's actually 0, 0, and then partial q partial x minus partial p partial y. So I'm not saying something radically different in this two-dimensional analysis. I'm just saying that the curl, when we look at 2 dimensions, it's just the condition that the difference of these partials is 0. That's the content of the curl being 0. What's that have to do with Green's theorem? Quite clearly everything, right? Like, that's the thing that appears in Green's theorem. So let's talk about this. Let's suppose then that we have a simply connected subset of the plane, right? And suppose we have the analog of the curl being 0 for our vector field, right? Can we argue that for what does 4 give us? Can we argue that 4 implies that, you know, the integral around a loop is 0? Like, assume. So here's the basically I want to talk about how the proof that 4 implies 3 is what we're going to do at the moment. 4 implies 3. So let's assume that a subset of the plane, is simply connected, which is just a fancy way of saying no holes, all right? And it's connected. All right? And we're going to assume that partial q partial x minus partial p partial y is equal to 0 for our vector field f, which is p comma q. What do we have to work with? We have Green's theorem, right? What's Green's theorem tell us? Green's theorem tells us that if we consider, you know, a loop, let's say, you know, L, which is the boundary of some disk, you know, which is where the disk is a subset of the U. Let me draw a picture. Did you guys ever think about the importance of drawing pictures? I was talking to Dr. Wang today. He said something very interesting. He said that there's a guy who's proved, he's got like a couple Nobel Prizes or the equivalent of a Nobel Prize. Maybe he's like a computer science type or something. And he's proved that essentially the human brain can only consider 7 plus or minus 2 things. So the brainiest brain can simultaneously consider 9 things at most. Me, probably 5. What's that? At a time, yeah. But Dr. Wang points out that we can easily draw a graph that has 20 things. So do you understand the importance of drawing things? The importance of writing a problem down? You're extending the scope of your understanding when you write things down. It's really important. That's why it's a very bad habit to just read the problem and start trying to do it in your head. It's a very bad habit. You're handicapping what you could be doing. Because simple paper and writing things out is expansive. Anyway, so here's my picture of you. Kind of like a pea, maybe a lima bean, I don't know. And then here's my loop, whatever, right? We're going to counterclockwise orient that thing, right? So my D is here. Okay, great. Now apply Green's theorem. It says that the integral around the loop of f dot dr, right, is equal to the double integral over the, you know, the disk, or it doesn't have to be a disk, whatever that is, of partial q partial x minus partial p partial y, right? dA. But what is that? That's given to be 0, right? So what's the integral of 0? It's 0. So what does this mean? This means the integral around this loop is 0. What loop was that? any old loop, right? So that shows you that 3 is true. And we've already showed the equivalence of like 1, 2, and 3 previously, right? So this was the missing link, if you will, in our logic of the previous discussion, because we didn't know Green's theorem then, right? But now we do. Okay, so that's one thing. But let's go back to the question of conservative vector fields. Let's think a little bit harder about that now that we've got a little bit more to play with. How do we decide whether or not a vector field is conservative? Let's take a look at an example. I want to show you there's really two paths to go down here, all right? We'll stick with 2 dimensions, all right? But the new idea I wanted to mention to you guys is the concept of locally conservative. Locally conservative. Let me give you a definition for that. What do I mean by locally conservative? So here's the definition. I'll give it. Let me give it in n dimensions. So if we, definition f, a vector field on Rn is locally conservative at P, a point P in Rn, if there exists some open connected set containing U, excuse me, containing P, all right, let's say U, all right, for which f is equal to the gradient of some function f at each point in U. All right, so like this is what we mean by locally conservative, is that you can find a potential at some points. All right, but the thing is, this is not to be confused with just conservative. Conservative, if a vector field's conservative, if it's conservative on its whole domain. So the standard example I always give of this, guys, is the following. So, because I'll do it over here. So I'm gonna kind of go backwards. I'm going to show you, if you will, the man behind the curtain of my previous example in here. All right. Consider f equal to the inverse tangent of y over x, right? What's the gradient of this? All right, so check it out. The gradient of f is, after some calculation, minus y over x squared plus y squared, x over x squared plus y squared. That follows because the derivative of inverse tangent is 1 over 1 plus the thing squared, and then when we multiply by the chain rule, we end up picking up this these terms. All right, so this short calculation shows you that in fact is the gradient of the inverse tangent of y over x. So, and then I integrate, let's see how to say this. So if I look at the vector field f, right, equal to this thing. This right here, this satisfies the condition partial x of the q, which in this case is x over x squared plus y squared, equals to partial y of the p, which in this case is minus y over x squared plus y squared, right? That's another way we can look at that condition, which I sometimes call the closed condition, but you see this is equivalent to partial q partial x equals to partial p partial y, right? So you can work both of these out. I think I read it last class even, right? These are equal. So basically, that makes you think that, this is a conservative vector field if you're not careful. But the problem is even though this is equal to 0, the question is context, right? Where is it equal to 0? So this holds for all x comma y not equal to the origin. So that's the problem, right? If I try to, look at a loop that is around the origin, right? And I try to do, okay, so like the integral of f dot dr is supposedly, equal to, the double integral, let me say this is c, equal to the boundary of d of, partial q partial x minus partial p partial y. Well, I'm just telling you that that's 0 for this vector field, right? So we get 0 here. And yet, what is that integral of f dot dr? I mean, so if you go around here, right? Wow, sorry. I mean, we calculated the integral directly. Yeah? For the unit circle, at least. The integral of minus y dx plus x dy over x squared plus y squared over, say, the unit circle, x squared plus y squared equals to 1. This is the integral from 0 to 2 pi of sine squared t plus cosine squared t dt divided by, well, cosine squared plus sine squared. In other words, it's 2 pi. This is completely unsurprising, because what is this vector field? Yeah.
Theta hat.
Theta hat, right. Is it theta hat? Not sure it's theta hat. I think you're right, because it's the unit circle. But if I had made this a different circle, I'm not sure it would have been theta hat. I mean, this is theta, right? So basically, what this amounts to is we're integrating the gradient of theta over the circle, right? So we're getting that the net change in theta is 2 pi. Of course it is, right? I mean, another way to look at this is d theta. So we're integrating d theta over the circle, and of course that's 2 pi. Yeah.
Making an amendment, it's theta hat over r.
Yeah, theta hat over r. I think that's right. Yeah. Cool. So what's the problem? Like, the problem is that I'm showing you is if we naively look at this, we've got 0, yet it's not 0, it's actually 2 pi, right? And the reason that we'd be wrong is because we can't apply Green's theorem when there's a divergent point inside. Right? I think I made this point yesterday, I'm trying to make it again. Now, but my larger point to you is that this vector field is not, okay, this vector field F, the question is what's its domain? Its domain is the punctured plane, right? It is locally conservative, right? It is locally conservative. Like, basically we have, notice that F is equal to the gradient of the inverse tangent of y over x for what? Certainly if we just apply it for x greater than 0, we could think about u equal to, say, x comma y such that x is greater than 0. Definitely F is conservative with respect to that right half plane. Right? And the right half plane is simply connected. Right? If you take any, if we think about the right half plane, any loop over here, right, I can deform to a point, you know? So the right half plane is, in fact, simply connected. But there's nothing in this formula, actually, that is about this singular, this obstruction we're getting in my thinking right now to the y-axis. That y-axis is not apparent in here. In fact, you could also write that the vector field F is the gradient of the inverse cotangent of x over y. And this would be perfectly good potential for the function if we just think about x comma y such that y is positive. So here you go. This is a potential energy function for your vector field on the upper half plane. Inverse cotangent you could use. All right? I use the inverse cotangent that goes from 0 to pi. Some people use inverse cotangent that's wonkier, but let's not do that. So locally conservative is not the same as conservative. You can have a vector field which is locally conservative everywhere on its domain, and yet it's not conservative. Because conservative, a vector field being conservative for its whole domain is an intrinsically what's called topological consideration. It requires us to think about the totality of the domain. And the ultimate thing that's spoiling it for us here is that, like, if you think through what I'm covering up at the moment, the problem is this. The angle function, right, as it cycles all the way around 0 to 2 pi, there has to be a place where you jump from like angle alpha. Well, so let's say the angle jump is 0. So you go from 0 to 2 pi, right? On the positive x-axis, you're jumping from 0 to 2 pi at that one point, right? So if you think about the angle function theta, it's got the property that as you go across the positive x-axis, it's jumping from 0 to 2 pi over an infinitesimal region. Is that continuous? No, that is not continuous. That is a jump, finite jump. But for the gradient to exist for a function, that means that function's differentiable. So you can't have a differentiable function all the way around the circle, because if you did, it would be continuous all the way around the circle. But you can't do that because the angle has to jump somewhere. It's unavoidable. Now, it's just an artifact of using inverse tangent that jump for us happened at the y-axis. Like, if you study that more carefully, it depends. Like, you can make it so that the angle function's continuous everywhere except for like one deleted line segment. If you study this more carefully, this actually is the thing which makes Math 331 difficult. Math 331 confronts this issue throughout this complex analysis class. The complex analysis class, a large part of what makes it interesting is the study of angle. And how do you assign an angle to a complex number? You see there's an infinity of choices, right? So as you study equations, like, you know this. I say the angle is pi over 4. What might you say it is? It's pi over 4 plus 2 pi, right? Or it's pi over 4 minus 2 pi, right? Those are other geometrically reasonable choices for the angle. So there's always a degeneracy in our description of angle, and that actually is what is a lot of what we're facing here in our analysis of locally conservative versus globally conservative. Now, you asked me a while ago about Gauss's law. Is this Gauss's law? And the answer is, well, sort of. So, let's see if I can get to it. So two-dimensional oh, come on. Oh, you know what? You have to plug it in. See here. All right. Do it. All right, there we go. So imagine we're studying electrostatics in 2 dimensions. A fundamental law of electrostatics is Gauss's law. Gauss's law says that the flux from the electric field that goes through a closed curve is proportional to the charge inside. This is Gauss's law. So essentially that gives us the charge per unit area, sigma. We have to integrate sigma dA. That gives us the flux of the electric field. Now, if we think about an isolated charge at the origin, it must have circular symmetry because there's no difference whether you're going this way or that way, right? So it follows then by the symmetry that this must be E times 2 pi r. And forgive me, we're using, oh no. I have a problem. I'm teaching another course that uses a totally different notation for spherical and cylindrical coordinates. At times, I bring you comments from that course. I'm deleting that comment. Let us continue. So 2 pi r times E is equal to Q. And so the electric field then, for a point charge in 2 dimensions, is simply Q over 2 pi r r hat. That's what Gauss's law says. And so that's consistent. If we calculate the flux of the electric field, we've got E dot n hat, which is Q over 2 pi r r hat dot r hat. Do. Look, Gauss's law checks. That's the right solution for Gauss's law. The flux is in fact proportional to the charge. Now, but then we can start doing some soul searching about Green's theorem in the divergence form. What's the divergence of the Coulomb field in 2 dimensions? Well, this is the Coulomb field in 2 dimensions. You have a problem in your homework, which has got an x squared plus y squared plus z squared to the 3 halves and an x, y, z. That's analogous to what we're doing, but in 3 dimensions. Anyway, and likewise, there you'll prove the 3-dimensional divergence is 0. Here I prove the 2-dimensional divergence is 0. The calculation is very similar. This gives us twice the radius squared minus twice the radius squared, so the divergence is 0. In your homework problem, you'll get thrice the spherical radius squared minus thrice the spherical radius squared, and so you get the 3-dimensional divergence is 0 in your homework. Anyway, so the flux of the electric field, there's a ds missing here, sorry, is equal to the area integral of the divergence. This is the divergence form of Green's theorem. That would imply, carelessly, that Q is equal to 0. But of course it's not. And the error of this calculation, we know. I've been talking about it. It's that the Coulomb field is in fact divergent. And by the way, the flux of the Coulomb field is the same as the work done by the theta hat field, theta hat over r field. Those are the same problem. So we haven't been talking about a different thing today. And so anyway, if you think about not just one charge, but a whole ensemble of charges, like n of them, put at different points, kadunk, 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 you're going to have a net electric field which has a divergence which is infinite at any one of those points, because wherever the divergence is infinite, it's a signature that there's physical charge which exists there. And so the net Coulomb field, we just take the sum of the Coulomb fields like this, and then if you calculate the flux from the net field, if you think about a little circle that encircles the kth one, you get charge qk, and it all works together. This is the theory of 2-dimensional electrostatics, and at the heart of it is, if you really want to understand it, you can repair Green's theorem by saying the divergence of r hat over r squared is actually 2 pi times the Dirac delta function of r. This is a way of building infinity into the mathematics, but that is not for this course. Anyway, I shut up. See you guys. Have a good weekend.